Okay, here we go. We're going to be taking a look at polar molecules and nonpolar molecules. My hope is that you watch this first and then you're going to see that there's a PowerPoint that you can kind of click through a couple slides, but a lot of times polarity is better just explained. So one of the things that we've been doing is building these different covalent compounds, also known as molecular compounds. We know they're molecular because they're made up of three or four or more nonmetals. So here we see nitrogen, and then we've got the three hydrogens, and then notice that lone pair of electrons. When you build this, you notice that it takes on a shape. And one of the things that we talked about is polar and nonpolar bonds, and we said that sometimes you've got these atoms that are more electronegative pulling harder on the shared electrons, which is exactly what we see right here with ammonia. We know that that nitrogen is more electronegative, and these wedges are actually representing a shared pair of electrons. So you have to think about that. Is the nitrogen equally sharing those electrons with the hydrogens? No, it's definitely not. The nitrogen is actually pulling harder, so those electrons that are being shared are actually spending more time with the nitrogen. And what you see me drawing here are called dipole arrows. And those dipole arrows are just the direction it's pointing to the atom that the electrons are spending more time with. Now, in saying that, if the electrons are spending more time with the nitrogen, that means that this nitrogen, we're going to say, is going to go slightly negative because the electrons are spending more time with the nitrogen, which means all these hydrogens down here are going to go slightly positive. And so what we see happen is two poles. You have a positive and a negative end to this molecule, making it a polar molecule. Same thing over here. We see the carbon is sharing a set of electrons with hydrogen, another hydrogen, chlorine, and chlorine. If you look back at the periodic trend for electronegativity, you remember that as you move to the right, closer to fluorine, those atoms become more and more electronegative. So when we look at this, are carbon and chlorine equally sharing those electrons? Absolutely not. The chlorine is actually pulling harder on those electrons, meaning the chlorines are going to go slightly negative. And then, of course, we're going to see a slightly positive in here. So once again, you end up with these two poles, making those polar molecules. Now, the water is one that hopefully you remember from biology. Again, you've got oxygen, who's definitely more electronegative than hydrogen. You also have these two lone pairs of electrons. And even over here, those lone pairs of electrons are, once again, you have to think pulling. And so we see that the oxygen here is pulling, not sharing equally, which means we see the oxygen go slightly negative and the two hydrogens are going to go slightly positive. This is why water is called a polar molecule, because you end up with these two poles, positive and negative poles. And the last polar molecule we see here, we still have carbon, we still have four shared pairs of electrons, but of course there's that chlorine definitely pulling harder on the shared pairs of electrons. So once again, we have that slightly negative, slightly positive. And so what I've just showed you here are four examples of polar molecules where we see an unequal sharing of electrons. Let's take a look down here at some non-polar molecules so you can see what would happen if those things cancel out. So here we have a carbon, and this is one where if you build this tetrahedral molecule, it'll really make a lot more sense. But we see that the chlorines, we know, are definitely pulling harder on all the electrons. But what happens in this situation, if you had physical science or physics, you learned a little bit about vectors, and vectors have to do with magnitude and a direction. And so in this situation, all the chlorines are pulling equally on the electrons, and so those forces are actually canceling each other out. And since they're canceling each other out, this is a non-polar molecule. All those different sides cancel each other out. Another way to think about this is think of the carbon. And if we were drawing this as a Lewis structure, here's those four chlorines around it. Well, if these two chlorines were pulling in these opposite directions and these two chlorines were pulling in those opposite directions, the carbon's not going to move anywhere, which is exactly what's happening here. Take a look over here. Remember, boron's a moron, and it's actually content with 6. We see that there's no lone pairs of electrons on that central atom. The chlorines are definitely pulling, but notice again, they're all pulling in equidistant directions with the same amount of force. Therefore, this is a nonpolar molecule because all those different forces cancel each other out. Carbon dioxide is one that students a lot of times get confused about because they see these lone pairs of electrons. But think about, again, almost like a game of tug of war. And carbon is right here at the center of that game of tug of war. This oxygen is a double bond, and obviously he's pulling on those electrons. This oxygen is pulling on those electrons. So even though here you have two polar bonds, the two bonds cancel out from each other, making this a non-polar molecule. They're both pulling equally in opposite directions, and so those two forces cancel each other out, and that ends up being a non-polar molecule. And then the last one we see over here, again, goes back to symmetry. We see the carbon, and we see those 4 hydrogens, and it's going to be just like this example over here, where all those different forces cancel each other out, and so also a non-polar molecule. When you flip through that PowerPoint, you're going to see a couple of things. And the first thing on polar molecules is that if you see lone pairs of electrons on the central atom, that is a huge indicator that it is definitely polar, okay? The second thing is that if it's not symmetrical, and some of these up here are kind of hard to see, but definitely right here, do you see how that's definitely not symmetrical? When you build that, there's no symmetry there. However, down here, you definitely have symmetry. And so characteristics of nonpolar molecules, one of the very first ones is going to be that symmetry. And second thing, no lone pairs on that central atom. Notice that I'm saying central atom because when you look at this, you see lone pairs of electrons that are not bonded. However, it's the lone pairs of electrons on the central atom that we care about. Again, here's oxygen, central atom, 2 lone pairs of electrons, it's polar. Nitrogen, central atom, lone pair of electrons, it's polar. And that's why drawing the Lewis structures on these and drawing that molecular shape can a lot of times help you identify if something's polar or nonpolar. So now that we've taken a look at a couple of these, I would encourage you to open up that PowerPoint, kind of work back through it, read through it, do the examples in the PowerPoint, and then take a look at the ones that are on the back of the molecular geometry lab that we did, and go ahead and try drawing your arrows and identifying what those different shapes are.